In an earlier video, when we talked about making ester enolates, I kind of alluded to the fact that your choice of base is important. So let's look again at an old reaction to kind of set the table for this discussion. So when we treat a ketone and we want to make an enolate from it, we can treat it with all kinds of bases. We've used sodium hydroxide, we've used things like sodium methoxide, we've even used something like sodium ethoxide, or that's an O-ethyl. And let's just lump all these, they're all the same thing. They're all sodium and an OR minus. And that R group, that R can be an H, it can be methyl, it can be ethyl, whatever. And they all behave in the same way. And they're all going to help us make an enolate. Yes, the equilibrium will favor the backwards process, but we can access our enolate. Great. What we haven't talked about is what other processes can happen in this reaction. And as it turns out, our OR group, because it's electron rich, it's not just a base, it's also a nucleophile. And it can attack our carbonyl. And we know anytime we make attack a carbonyl, we make a tetrahedral intermediate. Now, as it turns out, this tetrahedral intermediate can't do very much. It kind of forms, looks around, and then the O minus just kind of says, get out of here, OR minus, and it kicks it out, and we go right back to the starting material. So let's see how things are different when we try to do an ester. Let's pick out an ester. OCH3. Now we're going to treat it with our same base again, NaOR. Alpha hydrogen, we're going to deprotonate. Pluck off that hydrogen. And now we made our enolate. Who cares what the base is? It really doesn't seem to make a difference. It's a base. It was a base in the top reaction. It's a base in the bottom reaction. However, we have to be mindful of this reaction, which can also occur. So here is our ester. And we're going to treat it with a base. And sometimes that base will act as a nucleophile. So that nucleophile attacks the carbonyl carbon. This is going to make a tetrahedral intermediate, as we know. That gets us to here. Well, now our tetrahedral intermediate, this can do something. We have leaving groups present. And sometimes this electron density will push down and kick out our OR group. And that'll take us right back to our starting material, which is just fine. But sometimes we will kick out the OR group that happened to start on our molecule, this OCH3. And if we eject that OCH3 group, we will have changed what our ester is. It's called a transesterification. And normally when you're doing this kind of chemistry, we're trying to make ester enolates, this is a bad thing. You don't want to change your ester into a new ester. So how do we control this? Bad news for you, we can't. We can't control the fact that our base is also nucleophilic and it's going to attack our ester. So what we do is we just make sure that our base matches our ester. So if we have an OCH3 group in our ester, then we make sure that the base we use also is OCH3. And that way, when the base attacks, and it will, and we form this tetrahedral intermediate, if we happen to kick out our existing OCH3, we will have just replaced it with a new OCH3. And so we won't get a new ester at all. So when you make ester enolates, it's important to match your base to the OR group of the ester. Didn't have to worry about that with a ketone, but we do have to worry about it with esters.